Okay, so here's the lesson from the first day of Unit 2. So Unit 2 is on systems of equations. So today we started with notes. So go ahead and add this one to your notes. Oops. So we're going to solve this system of equations. Now, this looks a little different than what you're used to. We see 3 variables and 3 equations, but the process is still the same for solving. We can still use elimination here. Now this one, because they were nice to us and gave us z was already solved for a number, we can just go ahead and substitute that into the other 2 equations. So I'm going to do that. I'm going to substitute 4 in for z into the top equation. So 2x plus 3y minus 6 times 4 should give me negative 20. So if I simplify that, 2x plus 3y minus 24 is equal to negative 20. I might as well get that negative 24 over to the other side by adding 24 to each side. So 2x plus 3y equals, and then if I'm adding 24 to both sides, that's going to give me 4. So the second equation, negative 3x plus 5y minus substituting 4 in equals 9. So simplifying negative 3x plus 5y, if I'm adding 4 to each side, is going to equal 13. So now I have my system of equations, 2x plus 3y equals 4, and negative 3x plus 5y equals 13, which is just 2 equations and 2 variables, which is what you're used to doing. You're used to solving those, and we know that when we solve those, we can either use substitution or elimination. So why don't we just eliminate the x's here? So if I'm going to eliminate the x's, I'm going to multiply this top equation by 3 and the bottom equation by 2. So when I do that, I'm getting 6x plus 9y equals 12 and negative 6x plus 10y equals 26. So if I add those together, I'm getting 19y is equal to 38, which means y is equal to 2. So now that I have 2 of the 3 variables, I'm going to substitute back in here to get the third variable x, or the other option, which would maybe take a little bit more work, is I could put the 2 variables into one of the 2 originals and solve for x that way. But I'm going to go ahead and put it in the 6x plus 9 times y, which is 2, is equal to 12. So 6x plus 18 equals 12. So 6x equals negative 6, which means x equals negative 1. So when I solve a system of equations that has 3 equations and 3 variables, what I need to do is still write that answer as a coordinate point. It is a coordinate point just like if they were linear equations. So I still would write x goes first, y goes second, z goes third. So negative 1, then 2, then 4 would be my solution. Now, we did talk in class about what this would look like graphically speaking. So we know if these were 2 equations and 2 variables, they would just be lines, and where the lines intersect, that's a coordinate point, and that would be the solution. The solution is, the significance of the solution is it's the point where the 2 lines intersect. Well, here though, if we were to graph these are not lines. These are actually what we call planes. You probably remember that, talking about that a little bit in geometry. So basically, if you're looking at 3 planes, we have the x, y, z coordinate plane. Okay, which is 3-dimensional. So picture that what I just drew there is supposed to represent 3D. So we have the x, the y, and the z coordinate plane. And if I were to plot points on that, I would actually have my x plane, my y plane, my z plane, and where those 3 planes intersect is always a coordinate point. Okay, so if you're picturing this whole thing is a plane, and then another plane coming out here, and then another plane there. Those 3 planes intersect at this coordinate point. and that coordinate point in this particular problem is -1, 2, 4. Okay, now as far as the XYZ coordinate plane, we won't really do a whole lot with that in Algebra 2. That'll come later. But you should know that there is such a thing as an XYZ coordinate plane. It's a 3-coordinate plane. It is 3-dimensional, and where planes intersect in the XYZ coordinate plane is a coordinate point. That's really all you need to know about the XYZ coordinate plane for right now. Okay, so that takes care of that one. Now let's try this one. This one's a little more complicated because none of the 3 equations are solved for us. So we're going to have to do a little bit more work. So the first step of solving a system of 3 equations and 3 variables is to check to see if any of the equations can be simplified. And I'm noticing that first can. 4 goes into all of those numbers. So if I divide 4x by 4, I get x. And again, y, and again, z is equal to, when I divide 136 by 4, I get 34. Okay, next, the second equation cannot be simplified, so I will just copy it. And the third equation, same thing, cannot be simplified, so I'll copy it. If they could be, you should simplify them because it'll make things easier. After simplifying any of the equations you can, you're going to do a series of pairing up and eliminating a variable. When you pair up, you're going to put 2 equations together of the 3. And then when you pair up again, you have to use the equation you didn't use yet along with one of the equations you already did use. So in other words, if I start by pairing up the first and the second equation, then in my second pairing, I'm going to have to use the third equation because I haven't used that yet. And then in that second pairing, because I have to use the third, I will, but I'll use the third with either the first or with the second. It doesn't matter, but you do have to use the third in the second pairing since we didn't use the third equation at all yet. So we're going to start by pairing up the first 2, and we can decide which variable to eliminate. Now, looking at what we're going to eliminate, it probably would be easiest to eliminate the x's or maybe even the y's because that's going to be the least amount of steps. I'm noticing that because we have an x and a 3x and we have an x and an x. So when I compare the first with the third, so it's probably going to be easiest to eliminate x. So you can decide whichever you want to eliminate. I'm going to eliminate x, and I'm going to pair up the first 2. So if I'm pairing up the first 2 and my plan is to eliminate the x, and I think I'm going to multiply that top equation by -3. Which is going to give me -3x minus 3y minus 3z is equal to -102. And then I'll just copy the second equation, 3x plus 2y plus 4z is equal to 95. When I add those 2 equations together, I'm getting -3y plus 2y, which is -y. I'm getting 4z plus -3z, which is positive 1z. And when I add -102 and 95, I'm getting -7. So I have y plus z is equal to -7. Now I'm going to use that equation in a moment, so I'm going to keep track of it. I'm going to just circle it since we have all these different equations written here. Now I'm going to pair up. Again, I have to use the third, and I could pair it with the first or the second. Probably a little bit easier to pair it with the first since we already have an x. So we'll just multiply that top equation by -1 so that we can eliminate the x again. Now, we eliminated the x in this first pairing. Remember, in the second pairing, we also have to eliminate the same variable x. So again, I'm going to multiply that first equation by -1, which is going to give me -x minus y minus z equals -34. I'm going to copy the third equation, x plus 2y plus 3z is equal to 56. And now that I have the same opposite signs with same number coefficient, I can eliminate the x's. 2y minus y is 1y. 3z minus 1z is positive 2z. And 56 minus 34 gives me, 22? Okay, that I'm also going to use again, so I'll keep track of that. I don't want to lose it. Now I have what I'm left with after eliminating the x in both pairings is I have 2 equations and 2 variables. And they're the same variables. So at this point, it's exactly like problems that you've solved in the past, 2 equations and 2 variables. So you could either eliminate or substitute to solve for y and z. I'm noticing the negative y and the positive y, so that looks like it's going to be pretty nice to eliminate, which is what I'm going to use. Because I really don't have to do any work or multiply the equations by anything. I already have the same coefficient but opposite signs. So when I add y plus negative y, I am getting no more y's. 2z plus z gives me 3z. And negative 7 plus 22 gives me a positive 15. So that means z is equal to 5. So now I have z, and I'm not going to go back to the originals yet because I only have one variable. So I'm going to go back to either of these two that I boxed and substitute in z to solve for y. So I'll just go here to this first one. Negative y plus, I'm substituting in 5, equals negative 7. So negative y is equal to, subtracting 5 gives me negative 12. So that means y is equal to positive 12. So now I have y and z, and I need x. So now I am going to go back to, my choices are either one of the 3 originals, or I could use the simplified first equation, which is what I'm going to do because the numbers are smaller. So we had 1x plus 1y plus 1z is equal to 34. I'm substituting in, I don't know x, but I do know y is 12, and I do know z is 5, and that equals 34. So 1x plus 17 should equal 34, which means x should equal 17. Now I have my x, y, and z. Remember, these are planes, and if I graph them, the planes intersect at one coordinate point, and that coordinate point is 17, 12, 5. That is the solution to this system of equations. Homework for tonight is on pages 7 and 8 in the Unit 2 packet. Please complete that for tomorrow.